This is the intuition video for question 1I of the 2010 MAT paper. In this question we're given this horrible looking function here, IA, and what we're asked is, for a greater than 0, at what point is di by dA 0? So at what point is the rate of change of the integral with respect to a naught? Now, the first intuitive step to me at least is to have a look at what the function inside this integral looks like, which is y equals 4 minus 2 to the x squared. So let's sketch that. Now, the shape of this graph isn't too unexpected. X squared is an increasing function in x, so 2 to the x squared will be, so 4 minus it will be decreasing, and indeed that's what we get. However, the real significant part of this is this point here, the intersection with the x-axis. And that becomes clearer when we sketch the graph of IA. So we'll sketch IA against A and see what it looks like. Again, it doesn't look particularly significant at the minute, but now let's put this line, x equals the square root of 2. And you'll see there's a perfect alignment between these points. Now, why is that? Here's our original graph again, y equals 4 minus 2 to the x squared. And the area we're actually considering, we can consider as this. So we're basically working out the area of the blue shaded region as a varies, where a will be this point here at the boundary. So if we think about how this moves, when we actually get to root 2, because this graph reaches 0 at the square root of 2, then the rate of change of the area as we move across will also be 0. Because after this point we'll start considering regions under the x-axis, and so IA will decrease, but it's still increasing as we move along here, so the derivative is actually 0 here of IA, and that is why at the square root of 2 we have the perfect alignment between the 0 of this function and the turning point of this function.